Okay, well, let me introduce myself real quickly. I'm Alan Marshall. I work in the tutoring lab here in L218 in the library at CFCC, and I have for a couple of years working in math, chemistry, and a couple other subjects. Really enjoy working there, and if you have a chance, please come and visit us. We're currently open 9 to 3. But I wanted to talk to you all today about conversions, and I've run one workshop early in the semester that focuses really on the method. And we'll get into some of that, but this conversion workshop will also take a look at chemistry applications and a little bit more in depth of some of those applications that are helpful, especially in the medical field. But if you've had some difficulties with conversions in the past, or you just want to be sure you're moving forward into chemistry and math with some confidence, this video will help you. So let's start off with, and I like to explain types of numbers whenever I do these workshops because it kind of frames where we're at with the numbers we're using. So let's think about numbers in three different categories, three different types, excuse me. And the first is going to be categorical. So we use phone numbers like this as addresses, or address as phone numbers to categorize, list, and search for or relate information. Your social security number is something like this, but math is not principally used. It's like your zip code. It's really just a destination, a location, an identifier. Counts. So if you have number of people within a room, you have a dozen eggs, ice cubes, it's the amount of concrete something that we have. I have 5 fingers on my hand. I have one bottle of water. It's a substance that I can talk about, and it's physically represented in some way. So we know what 1 is when we're counting, because each individual object, etc., is going to be relatable by whatever we count it as. Fingers, bottles of water, marbles in a bag. Each thing has a set count for 1, 2, 3, number of pigs on a farm, right? So they have a physically established meaning when we're counting. So we understand what 1 is. That's an odd thing to say, the concept of 1, but let's get into this next type, and I think you'll understand why I bring it up. Measurements are slightly different. Number of inches, seconds, grams. Although we can count them in ideas, we don't have a physical relation to them all the time. So they measure physical or abstract concepts. And so concept of 1 is kind of arbitrary. And I use that word when we're talking about 1 as a measurement as opposed to 1 pig. So 1 yard can be applied many more ways than 1 pig can be applied, right? And that's kind of the difference between numbers that we're talking about. So if we continue on talking about this concept of 1, in the past, we had kind of an issue figuring out what 1 would mean. For a period of time, measures were often related to people, like a king, his arm or a foot, including the measure between elbow and wrist was often used as like a building measurement. But different people, different kings, would mean that you would have to change that measurement constantly, and that things would not be uniform. And so the ability for us to communicate measurements to other people as answers, as to be able to build with the same materials as everybody, and to be able to communicate those ideas, we need to be working with a standard. And so in comes our individual systems of measurements. And I'll get into that in just a second, but I wanted to break real quick on the goals and outline. It's just so we're aware of kind of the flow of what we're going to be doing here. So as I said before, for this presentation, I'm working on the assumption you have at least seen these units before. Gram, milliliter, liter for the metric system, inch, foot, pound for the US system. So I'm going to be kind of brief on those. And our focus is less about defining the units and really more on the process of conversion. But if you would like help with that, remember there is another conversion workshop that I do more in depth on the process of just conversions and those units themselves. So please contact Rosemary or look at our website for that as well. So our focus is, like I said, less about defining the units and more about converting. But at the end, I really hope you see that not just how useful they are, but you're using conversion factors in your everyday life all day long and probably haven't recognized it because you haven't seen it as that thought process or seen it in the way that I'm going to expose it to you. The conversion factors fill our daily lives constantly. So our US units, and US likes to be extremely independent, so we are different from the rest of the world in a lot of how we measure things. And the basis of this unit is inch, foot, yard, mile. For distance, weight, ounce, pound, volume, teaspoon, tablespoon. This one gets a little bit nuanced. Fluid ounce, cup, pint, quart, and gallon. You might have heard of the gallon man in school, and then as you start getting into the smaller measurements, these become important. Teaspoon, tablespoon, fluid ounce. If you're going to work into a medical profession, you're going to want to be able to convert between those as well as metric measurements as well. So we'll have a few examples on that moving forward. And then temperature, Fahrenheit. I'm not going to do temperature conversions today because it's really just a separate equation for each one, but those are easily found as well and are often included as part of temperature, or excuse me, conversion charts, and that I will show you. And then our metric units, which I love it, they're so easy. Gram, meter, and liter is really what you need to remember for most of them. That's weight, length, and volume. And those can be scaled up as they need to, but the nice thing about the metric system, and many of you have been exposed to this before, is that all units in the metric system increase off of a scale of 10, right? So every time you go up, it's a power of 10, which is extremely convenient, and it's the basis of things like scientific notation, which we use and will use in this PowerPoint as well to define some of the larger as well as smaller numbers. And that's why scientific notation is often used easily, is because it's a power of 10 system. Metric system is no different. So quick reminder about the metric system. I always like to bring this up just because I think it's so valuable. I still find people who have not been exposed to this simple device, and it's called a mnemonic device. That M is silent. You don't have to remember the name. That's not the important thing. The important thing here is this sentence: King Henry died by drinking chocolate milk. Very simple acronym sentence that you want to remember the first letter of each of it. So I've highlighted that so you can try and keep it in your head. And each of those refers to a section of the metric system, starting with kilo, like kilogram, kilometer, kiloliter, and then moving down all the way to milli. So it goes from kilo, hecto, deca. Base is the only odd one in there. Base represents the base units. So if we go back to metric units real quick, remember that our base units are gram, meter, and liter. So interchangeably, depending on what you're talking about, you want to put that into this mnemonic device at the base setting. Just right there. So you would have, grams, meters, liters, wherever, right here in the center. Deci, centi, milli, moving down. And the nice thing is we can use the simple phrase to move our values along the metric line simply by hopping from each value and doing the same with the decimal place within our metric equation. So I'm going to do some quick metric conversions. As I said, I'm going to go through these kind of quickly because I'm hoping you've been kind of exposed to this before, but we do go more in depth on this in the first conversion workshop. So if I'm looking to convert 30 centimeters into meters, I would have to take it to base, right? So I would need to take 2 steps to the left where meters would be. And if I do that with the decimal place, I'm left with 0.3 meters. So I hope you can see if I'm moving from centimeters, right, to, sorry, let's see, I was trying to clear that, yeah. If I'm moving from centimeters to millimeters, it's one step to the right, right? And so we just move that decimal one over. So metric conversions work extremely quickly. And you'll see as we get down into the conversion factors, US doesn't always work that way. A foot is 12 inches, right? That's already kind of breaking down that 1 to 10 power system, which is why a lot of the sciences use metric conversions most of the time. So it's important to be able to not only do metric system conversions within the metric system, but also to be able to do conversions between US and metric values. And so we're going to get into some of that too, especially with some of the chemistry. So let me show you one or two charts. First is going to be a conversion table. And conversion tables are just very convenient ways of organizing some of these conversion factors. And I'm going to explain exactly what that is here in a second. But these conversion factors, which are just equivalent statements, right? Like I said, you can look here at the top and it says, okay, so 1 foot is equal to 12 inches. We know that, right? 1 foot also happens to be, if we're converting between the metric system, 0.305 meters. I'm hoping you can see that. Erase that just in case. But the idea is that these conversion tables are just convenient ways of having a lot of these conversion factors for common conversions brought together for you. So if you are exposed to some conversion conversion problems, and you're not sure exactly what factor you should be doing, you can always come into the Learning Lab. We have this table and the table on the next page that we're always willing to hand out, show you, help you with, etc. Or you can look online and you can often find that information fairly easily. But having these is going to be very helpful with moving forward in any of the conversion problems that you do, especially between measurement units. Next is just going to be a visualization of the metric scale, and you can see the simplicity of it, but you can also see how big and how small numbers can get quite quickly. And that's kind of what I want to show you here. So here in the highlighted region is my King Henry died by drinking chocolate milk, right? And that goes from kilo to the thousand, from the 1,000 to the 1,000th, right? But, well, first, so our base is right here, grams, liters, meters in the center. And as you go up, you can see how exponentially larger it gets, right? 10 to the 0, or our base, is just going to be 1. 10 to the 1 is 10, and then as each one increases, it increases by a factor or a power of 10. And so you can get to numbers very quickly like quadrillion or septillion, which we'll actually see later on a couple times when we're talking about atoms. So, and that's all the way out here at the metric prefix yata, which is pretty wild. But the reason we use scientific notation is because we can, in chemistry, start representing things like numbers of atoms that are in that level of number, which I find absolutely fascinating. We basically have a shorthand for how we express that. So, but don't get too worried about things like IATA right now. Stay kind of at home working within the metric system here at King Henry, and it all works the same way consistently throughout. So as you get used to doing things up and down within this range, you can express that later into these larger forms very easily. So start here, and then we'll continue working with those metric conversions. But I really show you this because it's a wonderful show of how big and how infinitesimally small these numbers can get. Septillionth, that's incredible, incredibly small, right? 1 to the septillionth, 1 septillionth, that's wild. But we have to represent those numbers because they occur in nature in some way, which is fascinating. All right, so conversion factors. You're saying, like, what is that? Didn't Joe Rogan used to host that at one point? No, it's actually, like I've said, a statement of two equal values, like 1 foot equals 12 inches and 12 inches equals a foot. Forward and back, as the law of fact says, that rule runs, right? So it works backwards and forwards, no matter how I say it. So 1 foot equals 12 inches, 12 inches equals 1 foot, either way. So we can represent that as a fractional ratio, either as 1 foot over 12 inches or 12 inches over a foot, which is saying 1 foot per 12 inches or 12 inches per 1 foot. You might hear that word per, P-E-R, a lot moving forward and how people explain ratios to you. And if you start picking up on it, you'll realize, like, miles per hour, wow, that's right, that's a ratio. That is how many miles you're going over how many hours it takes you to go that distance. So like I said, you're already using conversion factors all the time in your daily life. Whether you're recognizing it, it is just a matter of seeing it, right? So let's see what we can see. So let's talk about application. How do we use a conversion factor? And it stays, the nice thing about this is it stays the same pretty much throughout. If you figure out how to use a conversion factor, it is a consistent method that you can apply and then make longer and longer chains of conversions in order to solve harder and harder problems, essentially. So we start with this one-step conversion factor, which is, let's say, 5 feet. We need to figure out how many inches that is. And so we have 5 feet as our original value, and this is a whole number. So any whole number can be placed over a 1, right, to form a fraction. The whole number is just, able to be placed over a fraction. It's not mixed or I'm forgetting what it is, improper fraction, excuse me. So if you have a whole number, you can place it over 1 automatically. So you'll see that I place pretty much all of these conversion factors over 1. So this is what we have, right? We have 5 feet. I want you to remember that word. Next, we multiply by our conversion factor, which we talked about on the last page, right? Which is 1 foot equals 12 inches, or 12 inches equals 1 foot. And to figure out which one we need to, which one of those conversion factors we need to use, we make sure that the measurement we are searching for is on top of the fraction that we use as our conversion factor. So here I had what we have on top as feet, and see how it is different from what I want, which is inches, right? Interestingly enough, when feet here and feet here multiply over each other, it's just like having 2 over 2. It cancels out, right? And what we're left with is what we don't have cancel out. So the words themselves almost do a little multiplication and conversion factors, but really you can think about this as what I have on the top of my first fraction, what I want on the top of my second fraction, and multiply that out. And that is going to equal 60 inches, right? 5 times 12 is equal to 60 inches. Okay. So that very basic structure is how conversion factors are always going to be set up. So let's see if I know you have another example here. So let's run through, because I'm going to do kind of 2 steps separately for this one. So you have a project which requires 108 inches of cloth, but the store only sells it for $15 per yard. How much will you have to pay in order to have all of the cloth you need for your project? So you know that you start off with 108 inches of cloth, right? So we need to convert that into an amount that the store sells it for. So what do we need? We need to find yards, right? If we know that 1 yard is equal to 36 inches, then we take what we have, multiply it by what we want. Let's get a little messy. And we're left with 3 yards, right? But we're not quite done, because the question asks us not only how many yards of cloth we need, it actually asks us for another conversion, right? And it asks us, how much will you have to pay in order to have all the cloth you need for your project? So we need to take our original answer, right, 3 yards, and we're going to move it over, and that's now what we have, right? And now what we want is to figure out how much to pay. And if it's $15 per, I should have put a yard there. I'm sorry, that's an editing mistake. $15 per yard, right? $15 per yard. Then yards is going to cancel out. We're left with dollars now as the measurement that we have. And we are told exactly how much we would have to pay for the 108 inches of cloth that is necessary for our project. Okay, so you can start to see how I took one factor, right, one conversion factor, and then immediately took the answer from that and plugged it into a second conversion factor. As we move forward, I'm going to start chaining those together in a method that's known as the train track method. And essentially, as long as you have those conversion factors in the right place, and they're in the right order to where what you have is being canceled out and what you want in each step is being gained, then you can set it up in a long chain, multiply multiply across the numerator, and then multiply across the denominator, divide, and you will be done. So that's the key method. It's setting them up. But first, you have to kind of understand how they work, figure out what the question's asking, map what I need to do, apply conversion factors, and you're good. Okay, so let's continue kind of doing what I'm talking about the method here, because I really want to hammer this, what I have and what I want home. So this is going to be the key thing to remember if you remember nothing else about conversion factors. Try and remember this: what you want on top of the first fraction, or excuse me, what you want on top of the second fraction, right? And then what you have on bottom of the conversion factor you were using, okay? And I think I might have actually messed up my, I messed up my colors here. I'm so sorry. That's a terrible editing mistake. So this should actually be the red, and this should actually be the blue. But essentially, look at this. Look at this. If I have 1 of what I have times 2 of what I want, the halves are going to cross out, and I will be left with 1 times 2, 2 of what I want. That really works for any system of measurement. As long as it's a standard system of measurement, as long as the conversion factor here is correct, as long as you are using a conversion factor here correctly, here in the middle, then this works every time, right? What I have is going to cross out. What I want is going to move forward. Okay, keep that in the back of your head as the method that we're applying through all of these and through any of these conversion factors. Okay, so all right, let's talk about volume. So volume refers to liquid a lot, but the reason it refers to liquid is because liquid maintains the space or takes the space of anything, any container with it that it is in. So if you have a bottle of water, say, you have water that fills it from the bottom to the top as much as it can and fills that space. So if I have a full bottle of water, measuring that the amount of water in it can give me the amount of space within that bottle when it's empty. So you need to kind of remember to connect volume and space always in your head, because it's not just about liquids, although you measure it most often, especially in chemistry, within milliliter or liter, which is obviously a quote-unquote liquid term. But you get your liter of cola, but you need to think of it as a volume measurement as well, or excuse me, a spatial measurement as well as volume. So thinking about it that way, if you are told to determine how many tablespoons of cold medicine are in a bottle that contains 250 milliliters of fluid, how would you determine the amount? So when I say map our conversions, and I'm going to say that a couple times, it's my method of saying kind of give yourself a path to the solution. And really that's what I'm saying. I want to say, what do I start with, right? What do I have? And then what's the next step going to be? And then the next step, and then the next step. So let me pull back up to our conversion factor table, and I'll show you. So moving from milliliters, so we're going to be down here in volume, we can move between milliliters and fluid ounces in the US system of measurement, but we can't move very easily milliliters to tablespoons, right? And that's what we're trying to get to. So you have to devise a path to how to get from milliliters all the way to what I have, right? So this is going to be the first real multi-step conversion that we do. So if we go back down to our problem, moving milliliters to US fluid ounce is something we can do. And then fluid ounces can convert to cups, right? So we're going to say that. And then our cup, which is about 8 fluid ounces, can be converted to tablespoons. And that's what we need to get to, right? Because we're going from this to this. And that's the key of conversions, is figuring out what's my start, what's my end, and everything in between. Okay. So what I say here is also fairly important. At each arrow point is where we're actually going to apply a conversion factor, right? So each of these, milliliters, fluid ounce, cup, are all going to be something I have at some point, as well as something I want, in the exception of milliliters. But at some point I'm going to have milliliters, fluid ounces, or cups, and I'm going to have to convert them at each of these arrow points. So what that is going to look like, I'm sorry I had to split this problem between 2 slides. I try not to do that as much as possible, but on occasion I want to just give you as much space to read it as possible too. So excuse me, if I set this up, we have 250 milliliters of cold medicine, right? Well, actually, I should probably circle the actual unit. It happens to be cold medicine. But milliliters, right? So we're looking at milliliters here. Just like we said, we're taking milliliters, and we need to get to fluid ounces. So we're going to, what I have crosses out, fluid ounces moves forward. Now I can go ahead and do the math on that and figure out how many fluid ounces I have, or I can start to set these up as a train track. And this is the first real train track we've shown, is moving across this. And it looks like a train track because if you set them up with lines, it looks sort of like a train could go over them. Kind of funny. Very, very minor point, not really important, but that's why I call it the train track setup. But you can just set this up, and as long as you have that map from our last slide, knowing that I'm moving from milliliters to fluid ounce to cup to tablespoon, from milliliters to fluid ounce to cup to tablespoon, as long as I follow that properly, and as long as each of these properly crosses out, so milliliters would cross out with milliliters, fluid ounces would cross out with fluid ounces, and I'd move on with cups. And then cups would cross out with the conversion factor and move on with tablespoons. As long as all of that works properly, then my answer is going to work. Okay, so you can multiply all the way across. So 250 times 16, I'd have to do it in my head again, but it's going to be at least 2,000, 3,000 or something, a couple thousand at least, and then divide by whatever 29.57 times 8 is, right? Because this is a 1 and this is a 1, and then just divide those two numbers, you will get 16.91. So if we're asking ourselves the original question, right? If you were told to determine how many tablespoons of cold medicine are in a bottle that contains 250 milliliters of fluid, how would you determine the amount? How many doses of tablespoon, or if the dose is a tablespoon, is in that bottle. And you can say you have 16 doses, you can administer 16 complete doses before you would have to require getting another bottle. And so if you're a hospital administrator, if you're a nurse, if you're someone who's in pharmacy, any kind of healthcare, if you have to do with administering doses, it's extremely important to be able to recognize conversion factors, to be able to do them, and to be able to do them between both US and metric measurements. So that's the first kind of big exposure I want to give y'all to that. And we'll do kind of some more medically related things moving forward. But that's the best example I can do on just dosage administration for a very easy liquid. So let's move into chemistry. And so I have this fun graphic. Let's take a breath. Chemistry often makes people a little bit afraid. I ain't it, but it's because I've tussled with it a little bit. Okay, so I respect it. So I understand. But chemistry can be our friend, and conversion factors are our absolute best friend in chemistry. And I want you to see that. So especially if you're moving into chemistry, if you're unsure about conversion factors, I really want to break it down as best we can. So let's get excited. Let's do it, okay? So let's talk about the big one. When you start talking about chemistry, you really have to start understanding this singular idea, which is Avogadro's number and the mole. And so thanks to essentially someone very smart, far smarter than me, far more chemistry and mathematically inclined, was able to figure out that within a certain amount of thing called a mole, that's a very funny name, a mole, like a little mole, but not. They defined this measurement of a mole as this certain amount of atoms. And this atom amount is called, or is not called, it's defined as 6.02 times 10 to the 23 atoms. So if you recall, when we were talking about yada, that was up at 10 to the 24, so only one step higher than yada is, so it would be 100 sextillion. So 6.02, 602 sextillion atoms in a mole, which is, you know, a massive amount. But when you're talking about atoms, you know, that's a relatively small amount, right? Because atoms make up, they're the building block of everything. So there's a huge number of them in even very small particles. And depending on the density, there can be even more. So that's getting into some other things. But the idea is that he wanted to define this amount of atoms, this gross amount of atoms, as a measurement, and so that we could standardize it, and so we could talk about it, and so we could relate it to other items within chemistry. And so this standard measurement became Avogadro's number, which is 6.02 times 10 to the 23, and the mole, which the mole is just a measurement of something. And you can have moles of anything, and that's where students start to get kind of confused on this concept, and I understand it. I understand why they get confused, because it's confused me too. That's what I mean. But you can have moles of anything, technically. 1,500 moles of puppies, absolutely, you could. I hope they're all totally fine. A full amount of puppies is 1,500. I hope I don't get like 4.5 puppies for that. I hope it's like 5 puppies. 128 moles of ice cream. Like I don't even know how much that is, but I'd love it. Just, you know, it's an amount of ice cream, right? It's that many atoms of ice cream. I don't care if it's a bite this big. I didn't actually do the math. You probably could. You can do the math to figure out exactly how much 128 moles of ice cream is if you understand the chemical composition of ice cream. I should have done that one for this one. That would have been funny. But most importantly, to chemistry is moles of molecules. So we'll talk about something like table salt later on. Table salt is sodium chloride, which is NaCl, right? And if you have a periodic table, which gives us a lot of information about every single atom, as well as the molar relation to something else, you can figure out a lot. So I might have stepped ahead of myself. So let's kind of catch up with my point here. So let's talk about Avogadro continuing. So the mole night. Say you wanted to find out how many atoms are found within 15 moles. I don't know why I have milligrams here. I'm so sorry. That is also an error that I'm going to have to write out. 15 moles of carbon. I think I started that as a milligram problem, and I wanted to kind of simplify it to make sure this point is clear. Then, in order to do so, you can find out exactly how many atoms are present within that or any substance simply by multiplying across this conversion factor, right? And so back to scientific notation. I hope you've been exposed to this enough. Scientific notation, once again, is a way of writing very large numbers very small. So this is 9.03 times 10 to the 24th, just like this is 6.02 times 10 to the 23rd. So if we look back at our metric only sheet, we're back here talking about something that's 10 to the 24th. That 9 yada, and so 9 septillion, 02, so 902, 10 to the 24th. That's how many atoms of carbon are within 15 moles. So quite a large amount. And once again, proof of why we need to use some of these, why we use scientific notation in chemistry is because we're representing numbers that are absolutely almost inconceivably massive, right? I can't think about how big how big a septillion is in amount of penguins, so I can't really think about it in the amount of atoms either. The same kind of idea. You can't do a solid count with it, right? So that concept of one is, once again, it's very odd, but those are very important. So, okay. I might be getting ahead of myself. I find that fascinating how we represent, these large and small numbers and just how crazy our calculations can get. It's one of the cooler things for chemistry and math for me. So yes, looking back at our metric sheet can show us just how high that amount is. It is in the septillions. That's the point I wanted to make. So, all right, Avogadro 3, the mole rises. Unfortunately, we cannot rely on getting our substance for chemical reactions solely in mole amounts, right? So I gave you in this last slide here 15 moles of carbon, not milligrams. I gave you 15 moles. But if you're in the lab, or in any kind of chemical process, you're really not going to be measured out in moles most of the time. It's going to be measured in a common measurement, usually milligrams or grams. And so you need to be able to convert between those as well. So I feel bad for doing this, but I think I actually want to skip this and come back to it because I want to give you a simpler introduction. So I should have rearranged this, but so let's just talk about converting from grams to moles requires, no, okay. I'm sorry. I explained this better this way. I remember why I did this. Okay. So for example, you were asked to predict the amount of atoms within a 10 milligram sample of sodium chloride, table salt, like we were talking about. In order to do so, you would need not only Avogadro's number, but the molar mass of salt as well. You're going to have to find a way, and the molar mass is the way that we connect, or the atomic mass and molar mass is the same thing, is the way that we connect something like sodium chloride or sodium and chloride in milligrams into moles. So that conversion factor is a separate conversion factor. And the tricky thing about that is atomic mass is a separate conversion factor for every single atom and every single compound. So H2O has a different molar mass than oxygen, et cetera, et cetera, et cetera. Fluorine has a different molar mass than potassium. Everything has a different molar mass. And every molecule, so So let's remember real quick that a molecule is several atoms put together. Like H2O is a water molecule. So it possesses the atomic mass of not only oxygen, but oxygen as well as 2 hydrogen. Okay. I know that some of the stuff I go very quickly on. Like I said, I'm hoping that you've had some introduction to at least some of this material before. If you have any questions, you can always join us in the Learning Lab or check back at the other conversion workshop or any of the other options that we have available. But getting into atomic mass, that's really the key, is remembering that for every element on the periodic table, every atom, at the bottom of each letter, or the name of that periodic element, that element, is a number right below it, and that is known as the atomic mass. So if you look at a periodic table, you would say, okay, right under oxygen, it says 16.001. So for the simplification of it, I'm going to just call it 16. What that is a mass amount of gram. Mass is weight, remember. Well, mass is more than weight, but mass is a weight measurement. Is an amount in grams over moles. So the periodic table is a huge list of conversion factors. That's what it is. It's a massive list of conversion factors, as well as a whole lot of other things that classify elements based off of a whole lot of other factors into periods and groups. But one of the major principal uses of the periodic table is as a massive list of conversion factors and a list for building conversion factors for using them in chemistry. So that's why when you get into chemistry, a good professor will tell you, keep that periodic table on you, mark it up, laminate it. It'll last you forever, because a well-marked periodic table, it's a very valuable tool for any chemical process. You will be using it consistently. So each atom in your molecule has its own atomic mass, and all must be added together to form the proper conversion factor. I think my next example is going to show that a bit more clearly. But when we go back and think about NaCl, right, that's sodium and chloride. So just like hydrogen and oxygen needed to be added together for H2O, we're going to have to do the same to find the atomic mass or the molar mass of sodium chloride as well. So remember our 10 milligrams of salt. Yeah, okay, perfect. We can calculate the molar mass conversion factor for NaCl as follows. And the molar mass conversion factor is just that. It's just the molar mass, right, of salt. And NaCl is just basic table salt. I don't think it's definitely not iodized, which you would buy at the store, but it is basic salt. So what you would go into is, okay, for every atom of NaCl present, Na present, or sodium present, you would have to add, the amount of its atomic mass. And if you look on the periodic table, sodium has an atomic mass of about 22.99 grams per mole. And then if you have one atom, and we only have one atom of each here, right? We only have one atom of sodium, and we only have one atom of chloride, or chlorine, it's not chloride. And so we can count 1 times that amount plus 1 times that amount, which 35.45 is chlorine's atomic mass, right? Which is going to equal together 58.44 grams of sodium chloride. So now they're together per mole, right? So for each of these, they would have been a conversion factor of 22.99 per mole for just sodium, or 35.45 grams per mole of just chlorine. But together, that factor changes. And that's what I mean when I say periodic table is a method of not only giving you all these conversion factors, but you have to build some yourself, right? Okay, so getting used to that is very important. Now let's use the molar mass and Avogadro's number, to answer our original question. We start with our 10 milligrams of salt, NaCl, multiplying across 1 mole, right? Because we want moles. Oh, there's my little clicker. There we go. We want moles, and we're getting rid of milligrams of ACl. Oh, I just realized that I should have made this 10 grams of NaCl. We're just going to pretend that is. Man, I got more errors than I really want to in this one. I deeply apologize, folks, for any difficulty that makes. Okay, so it's just a mistype. So if we have 10 grams of NaCl, over 58.44 grams of NaCl, moving that across, we would just multiply over the top, divide over the bottom. And if you do that, you're left with this amount of atoms total. So in 10 grams of sodium chloride, you would have this amount of atoms, right? Once again, this is also, you can see this is a train track conversion factor, right? As we move forward. And then you just multiply across and multiply across. And there's the train track. Okay, so I threw these in just so you have kind of a singular periodic table element and the backwards of it or the reverse of it. So if you have moles and you're trying to convert it out into grams, so you might have had a balanced equation or an equation that predicts a molar amount, and you're like, well, I like knowing the molar amount, it's very useful, but I'd really like to know how much gold or silver I'm getting. So in this one, it's silver. Silver is Ag on the periodic table. If I have 2 moles of silver, that's great, but I can't sell 2 moles of silver, right? I would have to sell it in a gram or a weight amount. So how much do I have? So I would use the conversion factor of 107.9 grams Ag, or silver, in order to take what I have crosses out, what I want moves forward. I have 215.8 grams of silver. Sounds much better to me. A, it's a larger number, but B, it's also something you could tell someone, like at a pawn shop or wherever you need to go. So how many moles is in 24.4 grams of gold? So if I was about to create a reaction, or if I needed to know just the molar amount, and I'm going to the next step is going to be what you do with molar amounts, really what you have them and the principal use for them. But you really need to see conversions first. But if I have 24.4 grams of gold, I can go from moles and I can go from grams using the factor, but it just flops, right? So now I have moles on top as the measurement that I want to end up with, and grams is going to end up canceling out. So 24.4 grams of gold, that's probably a pretty decent amount of gold, but if you had a 24.4 gram bracelet of gold, you just know it's all pure, whatever, 24 karat gold, and it's 24.4 grams. You technically have 0.124 moles of gold, as long as it's pure. I'm not a jeweler, so I don't know how pure actually a gold bracelet is, but you understand the concept. So now we're going to talk about this big word no one seems to like, but it's extremely important in chemistry. And we only have a couple more slides, but that's okay. So really this is the meat and potatoes, and I want to focus in on just the last bit of this real quick. So once you have what's called a balanced equation in chemistry, which means that this side, the reactants, is the same number of atoms in this side, the products. So you have the same number of carbon on the left as you do on the right, the same number of hydrogen on the left as you do on the right, the same number of oxygen on the left as you do on the right. Then you can use molar amounts to predict products, even if you only have like the reagent, right? So, or the reactant. So we can see that this is balanced, right? Because we have one carbon here, one carbon here. There's 4 hydrogens here, and then over here we have H2 times 2, so that's 2 times 2, that's 4. Then we have oxygen, 2 times 2 is 4, we have O2, and then 2O, so that's 2 oxygens, that's 2 oxygens, that's 4 oxygens. So this is a balanced equation, right? And it's very important. You cannot perform stoichiometry without it. This equation shows the process of methane burning. Methane is a very simple fuel. Cows release a lot of methane. There's actually a problem because this is actually a greenhouse gas as well. But we burn methane in a lot of different ways. One of the byproducts of which is carbon dioxide. Not so great. But one of the products is water, which is the other product that's produced. So you can see we have carbon dioxide here on the right as one of the products. But we're going to be concerned with this water because of the ratio. So if we are burning 1,000 grams of methane every hour. I'm pretty sure we do so over near the airport. If you've ever driven near there, there's a methane plant, or excuse me, a sewage water or wastewater treatment plant. I'm pretty sure they use methane disposal through burning, or at least releasing methane. So I think they do this process there. So let's say you're working over there. If you're burning 1,000 grams of methane at the water waste treatment center every hour, how much water is being produced? Pure H2O. You're producing some CO2, not good. But how much water is being produced? To do that, we need two very important things, right? We need the molar mass of methane. We've talked about molar mass. That's simply going to be taking the atomic mass of carbon and 4 hydrogens, adding them together. And then we need the ratio or conversion factor of methane to water, right? So that's been given. And that's the important part of the balanced equation, is if you look here, this methane has an invisible 1 in front of it, but this water has a very clear 2. So the ratio of methane to water is there's 2 water for every methane. That is another mole conversion factor. All right, that's an ugly way to show it. I've got it better on the next page. So here, so up at the top, we still have our conversion factor. I'm going to try and just sprint through these last 3 things. First, the molar mass we're going to be used is carbon is 12, 4 hydrogens is about 1 each. So we're going to say it's 16 grams of carbon or of methane per mole. And the molar mass for water, because we're also going to need that as well, is 18 grams per mole, because we have 2 hydrogen, which is essentially a gram each in atomic mass, and oxygen has an average of about 16 grams per atom. So we put our molar conversion factor, or excuse me, second we have our molar conversion factor, which we just discussed, right? 2 moles of water for every 1 mole of CH2, or CH4, excuse me. So this is 2 moles of water for every 1 mole of methane. So now we've got our big train track problem. Let's put it together. We start with 1,000 grams of methane that we're burning per hour, right? Let's put that per hour in there. I want to put that in there for this one. Okay, so it's not just over 1, it's over 1 per hour. 1,000 grams of methane is going to be 2,000, that makes it about 2,000 times 18, et cetera, et cetera. The math works out to be, oh, where'd it go? To be, I might have used too much of it. Oh no. Did my internet stop? Hello? Oh boy, technical difficulties, y'all. If you're seeing this, give me 1 second. I didn't kick anything, did I? Oh no. I was just about to finish up. Okay, perfect. Okay. It was telling me that I couldn't do anything. All right. Excellent. So I'm sorry, right here we were. If we multiply everything across the top, starting with 1,000 grams of methane, as long as we have set up our conversion factor properly, we would convert from grams of methane, right, grams of methane into moles of methane. Once something is in moles, we can use our molar conversion factor, right, this right here, in order to convert it into water. So the amazing thing is, across this chemical chemical equation. We've taken an understanding of the amount of methane and found an entirely different substance because it has a balanced relationship. And that is the key of conversion factors in chemistry. Okay, that's why I really wanted to get to that point, because now we're in moles of water, right? Moving forward, we're in moles of water. And so I wanted to then get the grams of water, so grams of water per hour. And then you could convert that into milliliters, however else you want to, which I probably should do. But the idea is this, that you can take this balanced equation between two substances. You could even figure out, based on the amount of oxygen you have, how much CO2 you could get, or whichever. Or, you know, you can find out the amount of CO2 based on the amount of methane, but it would be a 1-to-1 comparison. So I want you to start seeing that that is the basis of conversion factors in chemistry, right? Real quickly, I'm going to talk about limiting reagent. I'm glad I made this only in moles, because it's really just doing what we did, but you have to do it with two substances, right? So here I have two reactants. One is sodium, one is chlorine. They both form salt together. But because I have two and they are in with different ratios, right? There is 2 sodium for every 1 Cl2. So you would have to figure out, if I have, let's say, 6 moles of sodium and 2 moles of CO2, which is going to be the limiting reagent? Which one is going to run out first in my reaction? So if you're ever asked about limiting reagents, and you will be in chemistry, you'll figure out that it's like, why did my reaction go all the way to 6 moles of sodium chloride like I predicted, because I based it off of the amount of sodium I had? Well, the problem is because sodium makes up a large part of it, but it doesn't make up every part of it. And so if you only have 2 moles of chlorine, right, or chlorine gas, that Cl2 is chlorine gas, excuse me, then you're not going to be able to form as much table salt or sodium chloride as you would if you had them in the proper ratio, right? So for every, 2 sodium, you would need at least 1 chlorine. And if I have 6 moles of sodium here and 2 moles of chlorine, I only have 1 mole for every 3 moles of sodium, which is not the right ratio. So that's how limiting reagent works. And you would have to figure out both what chlorine is going to make with its amount and what sodium is going to make, or whatever your reactants are, in order to figure that out. Last few slides are just real quick on some real world applications. Stick with me real fast. So for those of you who are medical students, I wanted to throw this in. It's just an easy, not easy, it's just a quick understanding of talking about medication again. So let's talk about Greg, who has been diagnosed with diminished thyroid function. Thyroid has to do with how you process and metabolize food, and is prescribed a dosage of 0.150 milligrams of Synthroid every day. Synthroid helps your thyroid, let's say. So the tablets of Synthroid, we're told, contain 75 micrograms of Synthroid. Okay, so we have a microgram amount, but we have a milligram dosage, right? So we've already got a discrepancy that we're going to have to figure out. So that's one conversion factor. Thankfully, it's metric, so we can figure that out. Next, we need to figure out how many tablets he would take. So if the tablets contain 75 micrograms, how many does he need to take, does Greg need to take to be up on his medication, or to be properly following his medication? So once again, set up a map. We go from milligrams of Synthroid to micrograms, because that's what we're going to need to find out the tablets. And then from micrograms, we're going to go to number of tablets, right? So let's determine the necessary conversion factors, number 2. If we look at our metric sheet, and this is just, I'm just going to pull it out for you, is 1,000 micrograms per every milligram, right? So we're getting smaller, right? So that's why that gets bigger. And then for every tablet, we have 75 micrograms of Synthroid present. So for Greg's diagnosis, we're left with our conversion factors and our steps. We set it up like any other, right? even though it looks a little strange talking about tablets and all that stuff, each of those is just a conversion factor, and we can get the answer we need. So if we start with 0.150 milligrams per day, right? We have milligrams cross out becomes what I believe is 1, 2, 3, 4, like 1, 2, 3, yeah, 150 micrograms is what it's going to be at this point. And then times 1 and then divided by 75 is going to be 2 tablets. And because micrograms is crossed out, and tablets and day are still present, you could say that he should take 2 tablets per day, right? So the last thing I'm going to leave you with is how many conversion factors do you deal with on a daily basis, right? I already said miles per hour, and that's really kind of an easy one. But you have a speedometer that displays both kilometer and miles per hour most of the time. You go to Starbucks, you get a venti. It's 20 fluid ounces. That's why it's called a venti. They're being really fancy, but it's just 20 fluid ounces. And venti is the word for 20 in, I believe, Italian. And so 1 gallon of milk is $2.97. You can use that to figure out how many gallons of milk would cost something. One day is 24 hours. 1 hour is 60 minutes. 1 minute is 60 seconds. All of those conversion factors can be used. So I do this one real quick. If you want to travel again, currency exchange is a conversion factor. Taking the amount of money that you have $200 and you want to figure out how many euros you have. Like if the exchange rate is kind of low, you're actually gonna have less euros than you have dollars, but it depends on buying power. That's currency, but that's still a conversion factor. Time, 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute. That's 86,400 seconds in a day, right? That's how people determine that. And you can go backwards as well. And then this last one's just about food. So salmon is about 1.9% omega-3 fatty acids. So for every 100 grams of salmon that you eat, you can assume you're consuming 1.9% of that as omega-3 fatty acids, or 1.9 grams of omega-3 fatty acids. It comes into nutrition, it comes into every walk of life. So don't be discouraged by just chemistry conversions or math conversions. You're using this stuff already, and the better you can understand it, the more it will serve you as a boon. So thank you everybody for joining me today, online or otherwise. I really appreciate you taking the time. I know that the stuff can be frustrating, but seeking education is the best thing you can do for yourself. It's the most valuable tool you can give yourself moving forward. I truly believe that. So as always, if you think you can or you think you can't, you are right. Have a wonderful day. You know I love doing it. So if we think about other topics you need me for, just let me know. Otherwise, I'll just keep on refining these, and I'll bring them back, and whenever you need them, revise them, fix them up. I had a few kind of embarrassing typos that I need to fix, but I should have caught it. But beyond that,
I'm trying to work on the editing. I'm still trying to learn. They gave me Cortana, and so I'm still trying to learn that. It's a lot easier than YouTube to edit, but
yeah.
I haven't had any time to learn it yet, so it's kind of making it hard. But I know we can edit those parts out that we don't need.
Okay, perfect. Yeah, perfect. Because that point where I thought, I was like, well, maybe, it's like, no, I need to just, there was a reason that I put it in the order that I had it. I should have just, trust yourself, but that's okay.
I know, I mean, I've done it, so you're all set, like, wait, I put that there. I know.
Okay.
But you did a great job. I mean, I really love when you're, you did the drugs.
Yeah, and I really wanted to give it, like, you want real world application, like you said, that we wanted to have. It's not going to hurt non-medical students to get the medical, like, exposure, because conversion factors work either way, obviously, but I think that I wanted to make sure I had, like, let's talk about cold medicine, let's talk about tablets, let's talk about molar mass, conversion factors, chemistry, and make sure it's focused on these people who are seeing things that, that is relating to what they're studying. Because otherwise, like, how is that helpful?
Great,
You know,
great.
so
That was, I mean, I sat there and I'm like, wow, okay, that's really good. I mean, especially when you came out and you were talking about the thyroid, I'm like, wow. I mean, I've often wondered that myself, you know.
yeah, absolutely. How do they determine if you can understand, like, okay, a doctor tells you need this amount, a pharmacist is the one who has to figure out how to get you that dose in a different medicine. And so that's how they do it, is conversion therapies.
Yeah.
So
Hey,
it's
but
interesting.
even who wrote this part because that's where she's struggling with.
Yeah,
And so,
yeah.
you know, once we get it up and she can see it, I think it would be really
Mhm.
good when she comes to her exams because she's doing the pharmacology
Yeah.
program. So,
Well, hey, that's why we record it, you know.
yeah,
So,
yeah. So, well, thank you. You did a great job, really great job. And
absolutely, absolutely. Okay. Oh, I hadn't stopped recording.